Hi, my name is Anne-Sophie Maarten. I'm a PhD student at KU Leuven in Belgium, and I will be talking about a project we did on human embryo classification at the cleavage stage using deep learning techniques. Previous studies that automated embryo classification did this with data taken on day 5 of cultivation, which is known as the Blastocyst stage, whereas in clinical practice, embryos are usually transferred to a patient on the 3rd day of cultivation, known as the cleavage stage. And therefore, we wanted to see how well we could automate embryo quality assessments at this stage. And 3 relevant variables that embryologists look at when determining the health of an embryo at this stage are the degree of fragmentation, so the amount of fragments in the embryo, the asymmetry or the differences in size between different cells, and the number of individual cells in an embryo. And so we trained 2 different convolutional neural network architectures, a standard neural net that predicted the final decision, so whether to transfer an embryo to a patient if it is of good quality, or discard an embryo if it is of poor quality. And then a more complex branch neural network that predicted each of the 3 scoring variables that are indicative of embryo health. And our dataset was one of the largest so far reported in studies on automating embryo classification, with over 20,000 embryos in the training set and almost 2,000 embryos in both the validation and testing sets. And then for each embryo, we had multiple images taken at different depths of the cell. And therefore, we decided to try different image formats to see if it would make a difference in performance of the neural nets. So in the simplest case, we would train the neural nets on a single image per embryo, and in which case we would take the middle slice of each embryo. And in a more complex case, we would take 3 slices per embryo, and then we would either combine these 3 slices into one RGB image as separate channels, or we would store them as 3 separate grayscale images and train on a dataset 3 times as large. And we compared the performance of our standard neural network with a state-of-the-art model by Khosravi and colleagues, and they trained the neural net on data taken at the Blastocyst stage, so the 5th day of cultivation, and they achieved above 90% accuracy. And we wanted to see whether this high-performing model would also perform really well on data taken at the cleavage stage. But as you can see in this graph in light blue, their model named Stork did not perform really well on our data. In fact, our simpler neural network outperformed this complex neural network on data taken at the cleavage stage. And you can also see that the different image formats do not really make a difference for performance. So in general, our standard neural network performed around 75% accuracy. Then our branch neural network that predicted each of the 3 scoring variables achieved above chance level performance for each of these. But as you can see, the performance on the asymmetry variable was not really that good. Therefore, we did all subsequent analyses based on our standard neural network. Next, we looked at the batch effects, which is a known effect in clinical practice, because an embryologist would always determine which embryo to transfer to a patient based on a set of embryos from that same patient. And he or she will choose the best embryo out of the set to transfer to the patient. So we wanted to see whether our neural network would perform better if it had to make 2x2 comparisons of embryos from the same batch or the same patient. And as you can see, this improved the performance of our neural nets to above 80% accuracy. Next, we wanted to see whether our network performed better on easy cases, because some previous studies on automating embryo classification report their performance based on low quality or high quality embryos, and they exclude fair quality embryos. So we wanted to see how well our network performed on obvious discard cases or obvious transfer cases. And in this graph, you can see in light blue that the embryologist makes the obvious decision over 90% of the time, whereas our neural network makes the obvious decision 95% of the time for really low quality embryos and 85% of the time for really high quality embryos. And then lastly, we wanted to see how our results related to pregnancy outcome. And we checked whether there was a correlation between the predictions of our 8-layer neural network with implantation rates and we found a correlation of 0.64 with an explained variance of 0.41. So in conclusion, automated quality assessment at day 3 could achieve similar performance levels than previous studies have shown at day 5, and it would be worth it for future work to invest in datasets with scorings from multiple embryologists for each embryo, or data from different clinics, or even time-lapse image sequences to better model the development over the 3 days of cultivation. So if you'd like to know more, you can have a look at our poster, or feel free to contact me if you have any further questions. I would like to thank my collaborators, and I would like to thank you for taking the time to watch this video. Thank you and have a great day.